We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Mars, Earth's closest neighbor. For centuries, we've studied the red planet. A small fleet of orbiters and rovers are currently on the prowl, examining the planet for clues to the big questions. Was there, or is there, life on Mars? Mars's exploration is entering a new era. The Mars Reconnaissance Orbiter is circling the planet at the start of an extraordinary 5-year investigation. MRO will solve old mysteries, generate new insight, and ultimately peel back the cosmic veil, revealing Mars. Our understanding of Mars is getting greater by the day, and that understanding will be greatly enhanced by the Mars Reconnaissance Orbiter, or MRO. Launched from Cape Canaveral on August 10, 2005, MRO flew more than 160 million kilometers, reaching Mars in March 2006. Mounted on the 2-ton orbiter are the latest tools in cosmic spyware. They include instruments that will return detailed images and huge amounts of data about the atmosphere, surface, and subsurface of Mars. Two large solar panels power the orbiter, creating a 14-meter wingspan to absorb the sun's rays. A high-gain dish antenna will rapidly beam back vast quantities of information. Putting this $450 million payload into Mars's orbit required the dedication and skill of hundreds of NASA personnel around the globe. The two men that lead the MRO team are project manager Jim Graff and project scientist Richard Zurich of NASA's Jet Propulsion Laboratory. Once the MRO reached Mars, the first critical task was to slow the spacecraft to just the right speed to insert it into orbit. Jim Graff oversees the mission control staff at JPL. Dr. Graff and his operation team monitor and direct every move MRO makes, including entry into a successful orbital trajectory.
Peter, how's the spacecraft doing?
Spacecraft is all quiet.
They also coordinate all data transfer with both domestic NASA teams and international space agencies.
MRO required about 1,000 people over 5 years to bring it together and get it launched. And it's going to take another group, about 300 or 400 people, to operate it, to make sure that it accomplishes what it set out to do. That is, get to Mars and get all the science data back down and analyze it. It's a vast challenge. You have a lot of people that all have to do their jobs properly for the whole team to succeed.
Success is not a foregone conclusion. Over half of all spacecraft sent to Mars have failed, crashed, or spun out into space.
25,000 feet.
Everything went according to plan, and the spacecraft swung out 43,000 kilometers on its first 35-hour orbit. The elliptical path brought it within 250 kilometers of the surface on the return leg. With each orbit, MRO slows further from its top speed of 18,000 kilometers per hour, and the orbit shrinks to an almost circular one.
What we have to do is get that 35-hour orbit down to about 2 hours. And we do that by a technique we call aerobraking, where the spacecraft itself just grazes the top of the atmosphere of Mars. And it uses the friction with the molecules in the atmosphere to slow itself down, akin to what it might be if you were riding a bicycle and you extended your arms to help slow yourself down.
In March 2006, the Mars Reconnaissance Orbiter started traveling around the Red Planet. Over 7 months and more than 500 revolutions, MRO will settle into a cruising altitude roughly 300 kilometers above the planet, lower than any previous orbiter. In November 2006, scientists will activate MRO's instruments. Dr. Zurich leads the MRO's science team.
This is a half-scale model of the Mars Reconnaissance Orbiter. To give you an idea what
He and his colleagues are anxious to start the primary science phase. The 6 principal instruments on board will generate a great deal of data. The ultimate goal? To find evidence of life on Mars.
What we're looking at here is the payload deck. Now this would be facing Mars once we're in orbit around the planet. This is our big telescope, the HiRISE instrument. This is a very high-resolution imager. This is the device where we get the best resolution, where we go in and look at the details of what's down on the surface. To see the area around it, we have the context imager. CTX, this instrument has a broader swath, lower resolution. It provides us that regional coverage. This instrument, the Mars Climate Sounder, is looking at how things change in the atmosphere over a full annual cycle in terms of what's the temperature of the atmosphere, what water vapor is there, what dust is blowing around in the atmosphere. Now we have another weather instrument. It's a camera, and it's looking horizon to horizon. We sort of get an orange peel on each of 13 orbits a day. We put those together. You got a daily global map of the weather on the planet. This instrument is CRISM. This is our imaging spectrometer. And what we're doing with this is to look at the composition of the surface, because we want to see not only its shape, but what it's made of. On the backside of this spacecraft, we have another instrument, which is SHARAD, the shallow radar, which penetrates into the surface to look for layers of ice. We want to see things in detail, the shape of the surface. We want to see the composition of the surface. We want to see what's in the atmosphere and how it interacts with the surface. So being able to point our instruments and to take images and the composition measurements all at the same time is an important part of what we do.
While the payload aboard MRO is more sophisticated than previous orbiters, the satellites that paved the way for it provided valuable insight into Mars. 3 veteran spacecraft are still probing the planet from its upper atmosphere. Since 1999, the Mars Global Surveyor has completed more than 20,000 orbits and recorded nearly 140,000 images of the planet. In 2001, the Mars Odyssey's infrared cameras began creating detailed maps of Martian minerals, recording surface temperatures and analyzing atmospheric composition. And in 2004, the European Space Agency's Mars Express began tracking the rise and fall of the planet's polar ice caps. Using its subsurface radar, the orbiter also began peering beneath the Martian mantle to detect deposits of water ice kilometers beneath the red surface. MRO's instruments were designed to both complement and improve upon the capabilities of these orbiters. But one of the greatest contributions of the existing orbiter fleet was paving the way for 2 little geologists to reach the Martian surface. When the Mars exploration rovers Spirit and Opportunity bounced onto the Martian surface in 2003 and 2004, the foundation for their success had already been laid by the small fleet passing overhead. Working from aerial photographs and spectrometer readings, NASA scientists were able to determine the safest and most geologically interesting locations for the rovers to land. The Mars Reconnaissance Orbiter will sharpen our view and understanding of the Red Planet like no other spacecraft. For decades, the resolution of Mars's images captured by telescopes and orbiters was far too low to reveal the finer surface details that scientists sought. The Mars exploration rovers Spirit and Opportunity added something new: the ability to move and explore different areas.
Wait approximately 20 seconds from now.
These robotic surrogates opened their mechanical eyes in 2004, giving us an entirely new perspective on the planet.
Oh.
A view like no other. A 360-degree panorama from the Martian surface. Suddenly, Mars snapped into focus. A rusty, rocky surface pitted with massive craters and buttressed by extensive mountain ranges. The two rovers were sent to find out if conditions in this seemingly barren wasteland could have supported life. They prodded, poked, drilled and analyzed Mars's rocks, searching for evidence of liquid water, the key ingredient for life on Earth. The rover Opportunity arrived first. It made an interplanetary hole-in-one, landing inside a small depression dubbed Eagle Crater, close to a thin outcrop of rocks. After just a few weeks of close inspection, NASA scientists broke news that amazed the world.
We have concluded that the rocks here were once soaked in liquid water. This is the kind of place that would have been suitable for life. Now, that doesn't mean life was there. We don't know that. But this was a habitable place on Mars at one point in time.
Since there had been flowing water, life could have existed on Mars. NASA had its goal: chase the liquid water and search for conditions that once might have supported life on or beneath the surface. Mars is only about half the size of Earth, but it has about the same amount of dry land, roughly 150 million square kilometers. So NASA researchers needed to step back and take a much broader view. They needed a tool that could photograph, map, and analyze vast areas of the Red Planet in unprecedented detail. By the spring of 2005, that tool was taking shape in the form of the Mars Reconnaissance Orbiter, a spacecraft that could glean much of the same detailed information gathered by the rovers on the ground, but from an orbit about 300 kilometers above the surface. No longer would scientists be limited to a few points on Mars. Now they could examine the entire planet. At a Lockheed Martin facility in Colorado, MRO went from the drawing board to become a 2-ton reality. It took 5 years and hundreds of specialized personnel to design the orbiter and construct the instruments for its multi-purpose payload. MRO project scientist Richard Zurich was on hand to see the orbiter's high-precision camera mounted to the spacecraft.
Each time we've taken a new generation of instruments to Mars so that we could see finer detail than we could see before, we've seen new phenomena. We've answered some questions and we found out that what we thought Mars was not the way Mars is. What makes this orbiter unique is we're going to look at Mars in detail that we've not been able to do before. This orbiter is meant to bridge between our extended coverage that we have from previous orbiters down to that higher resolution that we've seen, but just in a handful of sites. We're trying to connect the dots and find out where the best place to go to the next lander. Is it back to the same sites? Maybe not.
That improved resolution will come from MRO's HiRISE, or High Resolution Image Science Experiment. It's the largest instrument on the orbiter, weighing close to 70 kilos, and is the most powerful camera ever sent into orbit around another planet. Previous Mars orbiters were able to identify something roughly the size of a dinner table. But from MRO's low-altitude orbit, HiRISE will be able to detect an object the size of a beach ball. One of the instrument's designers, Laszlo Kasthalia.
This rock here is about the size of rock we can reliably see with the camera on the Mars Global Surveyor spacecraft that's in orbit around Mars today. And it's about 15 feet across, and it's a good-sized boulder. However, with HiRISE, we're hoping to do better, about 5 times better, and be able to detect the rocks that are about this size here. This is about 3 feet across. Now, one of the nice things about HiRISE is that it's taking these high-resolution pictures in color. We have a lot of science interests on Mars, but one of them in particular is looking at what water's been doing. When especially hot water reacts with rocks, it can change the rock's colors. So here we have a rock that's been altered to a red color with the hot water that's run through it. Hot water can do different things and change rocks to a green color as well. And so with HiRISE, we can see where the rocks have been altered these kinds of different colors and see what the water's been up to. And that should hopefully help direct future missions to the places where the water's been doing the most interesting things on Mars.
HiRISE will photograph key areas of the planet, focusing its lens on 1% of the Martian surface. It will work in tandem with MRO's context camera, or CTX, which will scan broad swathes of the surface at a much lower resolution than HiRISE, looking for areas that pique scientists' interest. On previous missions, CTX would have been the high-resolution camera.
This was the best resolution that we had.
Richard Zurich can show how the two cameras work together using a photo mosaic compiled from previous orbiters.
You had bright areas and dark areas, and we thought we understood what these things are. But when you look at it at greater resolution, suddenly you see what it really is. The dark spots are sand dunes, for instance. The detail that you can see is from our best resolution with our current spacecraft. HiRISE will be able to get a factor of 3 or 4 better. But the context imager is meant to get this over an extended area.
Once CTX identifies a target, HiRISE will zoom in for a closer look.
We'll be taking very detailed looks at small patches within the larger context pictures, and we'll be able to give more detail on how the color variations are distributed on the ground.
Until now, this degree of detail could only be produced by cameras aboard the Mars exploration rovers patrolling at ground level over a relatively small area. HiRISE will collect similar detail from orbit for virtually any point on the planet.
One of the other unique things that we'll be doing with HiRISE is taking stereo pictures. So by taking 2 pictures of the same area, we'll be able to build up a 3D topographic model of that part of Mars. So we'll be able to see the rocks and boulders in 3 dimensions, not just a single flat picture.
Although the camera's 50-centimeter primary mirror has a field of view spanning just over 1 degree, an average HiRISE photograph will cover an area roughly 6 by 13 kilometers.
Now each individual pixel covers a tiny part of the ground, only about 1 foot across. So you need a whole lot of pixels to cover that ground. In fact, you need over 1 billion pixels. And so one of our big problems is getting all those pixels out the back end of this camera onto the spacecraft and eventually back down to Earth.
The massive amount of data generated from each image will be sent to a highly sensitive array of receivers set up for the Deep Space Network. MRO will transmit its signals to 3 main communication facilities in California, Spain, and Australia, and eventually onto MRO headquarters at the JPL in California. Even though MRO's radio transmission speed will be 10 times that of previous orbiters, processing these massive photographs will take weeks. But these new looks at Mars should lead scientists to target rich zones on the surface. The camera will zero in on deposits and landforms created by geologic and climatic processes. It will assist NASA scientists in determining the geological history of Mars, including the origin and age of surface gullies, polar layers, and volcanoes. Ultimately, all of this information and the stunning detail provided by HiRISE will also be used to digitally map new landing sites for future Mars missions.
We'll see sand dunes blowing across the surface. We'll see the polar caps and how they change in more detail than ever before. We'll be able to look at where the lava flows have gone and how they've run over the ground in places where the ground might have been wet when those lava flows are going, where there have been steam explosions. It's just gonna be a ton of fun.
The Mars Reconnaissance Orbiter won't begin the science phase of its mission until it finishes aero-braking into a final cruising orbit in November 2006. But once in that orbit, MRO will spend 5 years scanning the Martian surface. Its primary objective? Searching for evidence of liquid water, the key ingredient for life on Earth. Throughout 2004, NASA's Mars exploration rovers uncovered astounding new evidence that liquid water once covered parts of the Martian surface. The rover Opportunity made one of the most startling discoveries after it moved to a large crater named Endurance. Drilling into some rocks, the rover uncovered evidence that the planet had been repeatedly bathed in liquid water.
What we've determined is that first the rocks were deposited in a shallow, salty sea, where that salt is more like Epsom salts than our kind of salty oceans on the Earth. And then after that, they were soaked again in groundwater. And finally, after the rocks were buried and soaked in the groundwater, there was an impact. We don't know when that impact occurred, but it formed this crater. And then we discovered that after the impact, there was again some water. So water was around for quite a long time here.
The rover's Spirit and Opportunity confirmed that this barren landscape could once have given rise to life. As a result, MRO will search for other rocks like those found at Endurance Crater from its orbit some 300 kilometers above the surface. It's a tall order, but this spacecraft has a powerful instrument that can determine the mineral composition of Mars's rocks. The Compact Reconnaissance Imaging Spectrometer, or CRISM, will analyze light reflected from the Martian surface. Its sensors can see the individual color components across the spectrum from visible light to infrared. Since every mineral reflects a unique color signature, CRISM will be able to map the exact composition of the Martian crust. The spectrometer will help scientists zero in on rocks that have been soaked in water in the past. It may also locate hidden deposits still containing water. NASA developed CRISM from a similar remote sensing device that is in use on Earth. It's a spectrometer called AVARIS, and it's been used to map everything from the mineral composition of volcanoes in Hawaii to the dispersion pattern of debris at Ground Zero in New York City. The instrument is mounted aboard a plane that can maintain a steady heading over target areas at a constant slow speed of about 150 kilometers an hour. NASA scientist Dr. Robert Green and his colleagues designed AVARIS. Today, they're putting it to work over the deserts of central Nevada.
This is the AVARIS instrument. It measures images, photographs of the Earth's surface, but instead of just 3 colors like our eyes sees, this measures 224 colors. And with those 224 colors, we can actually see the interaction of the specific molecules with light and map the molecules. A spectrum is very analogous to a fingerprint. If we see the spectral shape of a certain molecule, then we know that molecule is present, whether that's a carbonate on the planet of Mars, which we would like to find, or whether it's vegetation here on the planet Earth. Today, we're going to take the AVERS instrument and we're going to fly a site south of here called Cuprite, Nevada. It's a hydrothermal system. And we will image this site and look at the molecular maps that the instrument produces and make predictions about what we'll find on the surface. Then later we'll go on the ground with a field spectrometer and confirm that this instrument is accurately predicting what's present on the Earth.
The AVERS optic system is mounted in the base of the plane and looks straight down on the Earth. Light reflecting off the surface hits a 36-centimeter mirror and is channeled through the spectrometer. The data is processed and then fed into onboard computers for analysis.
AVERS is healthy. Do a Navinet? Yes, Navinet run.
As the team flies over Cuprite, AVERS takes a mile-long photographic strip of the Nevada desert. In less than a minute, the system collects more than 1 million spectra.
Here's the imagery of Cuprite, Nevada. Your eye would see it, you can't tell what the surface mineralogy is. But if we jump into the spectroscopy, we can map the distance to those molecules.
Each mineral found on the ground produces a specific color on the screen. When the CRISM spectrometer scans the surface of Mars, scientists will be able to pinpoint high concentrations of water-related minerals like the ones seen here.
We can see the clays that tell us that that's a hydrothermal system. And if we look over into these hills of Goldfield, we actually see carbonates. We see the mineral calcite, which tells us carbonates are present. Almost everywhere on the Earth where you find carbonates, you find fossil evidence of life. We would love to find carbonates on Mars, and this is the technology that will help us answer that question.
CRISM's ability to accurately map large swathes of mineral deposits from space will allow scientists to hone their search for water and possible signs of life on Mars. The carbonates, clays, and salts found at sites like this here on Earth will be important targets for CRISM on Mars. They provide the best hope for discovering where liquid water once existed on the red planet.
Looking for the special spots on the surface of Mars is like looking for a needle in a haystack. We need to know where to go with the future rovers. CRISM will provide us that information because it will tell us exactly where the molecules of interest are that we want to follow up with future rover missions.
Mars is an extremely inhospitable place. Winds at the surface average 130 kilometers per hour. Dust storms can flare up and cloak the entire globe from the sun for months. The atmosphere is over 95% carbon dioxide and can't retain solar heat. The frigid temperatures of the surface swing from -50 to -130 degrees Celsius. One of the main scientific objectives of the Mars Reconnaissance Orbiter will be to advance the understanding of climate changes on the planet.
Our first emphasis is 1 Mars year of scientific observations. Why a Mars year? Because you get to see all the seasons, and that's an important climate signal that we're trying to capture. In fact, if there's one thing that we want to learn, it's how has climate of Mars changed over time?
In the past, Mars had a warmer and wetter atmosphere. NASA scientists want to retrace the history of liquid water on the surface and examine the conditions that led to its disappearance. They also hope to understand how dust storms, lava flows, and the advancing and receding polar caps have altered the geology of the planet. The success of future robotic and human exploration will rely heavily on MRO's ability to characterize weather conditions on Mars and prepare for them. The orbiter is equipped with 2 weather instruments. The Mars Color Imager, or MARSI, will act as the spacecraft's meteorologist. This camera will provide daily weather maps for the entire planet, just as satellites do above the Earth. It will track environmental changes at the surface. Using a series of light-sensitive filters, Marcy will be able to identify the composition of clouds, examine variations in the ozone, and track the rise and fall of ice at the polar caps as it orbits the planet every 2 hours.
It's looking horizon to horizon so that you get an orange peel along each of 13 orbits a day. And when you put that together, you've got a global map daily of the weather on the planet, and then we monitor that for a full Mars year.
The Mars Climate Sounder, or MCS, will track water conditions not only on the ground, but also any water vapor suspended above the surface. MCS will study the atmosphere in both the vertical and horizontal planes, monitoring dust levels, wind conditions, and solar radiation. The combined data from Marcy and MCS will be converted into three-dimensional global weather maps for both day and night.
This is a model of the Mars Climate Sounder. It's currently bolted on the bottom of the spacecraft, which is...
NASA scientist Dr. Daniel McLeese is responsible for the instrument.
The sounder has 2 telescopes. These are operating in the infrared wavelength region of the spectrum. These telescopes both look out at the atmosphere and at the surface. These large mechanisms are in fact the motors that, on command from the Earth, actually rotate the telescopes inside the drum. We do a bit of a dance, something we call the buckshot motion, in which as we spin over in our orbit, the polar caps, the instrument begins to look in all kinds of different directions. The Martian atmosphere is very much like the Earth's stratosphere, well above where airplanes fly, 100,000 feet and above. The characteristics are low density, which means that the atmospheric pressure at the surface is about 100 times less than it is on Earth. It's an atmosphere that in some sense is simpler than the Earth, and in some sense it is complex because the processes are different and we're learning about them for the first time.
Looking forward to future missions on Mars, Dr. McLeese hopes that Marcy and MCS will effectively predict weather conditions on the planet to protect both man and machine.
Someday, humans will move about the surface and live and operate, and one of the things that one will want to do is to be able to forecast changes that might adversely affect the way in which they work or even their health. And on Mars, that change is the rapid development of dust storms. And those dust storms can effectively reduce the sunlight on the surface. Certain kinds of vehicles that operate with solar energy aren't as efficient. It can make difficulty in seeing long distances. There's a lot of things you want to worry about.
The NASA orbiter, Mars Global Surveyor, has been recording dust activity in the atmosphere of the red planet for over 6 years. NASA has compiled data in a movie format that best illustrates the overwhelming effect a global dust storm can have on the surface.
We've got the planet unwrapped here, longitude this way. We've got the South Pole, the North Pole. We have a color chart that shows small amounts of dust in the blue, severe amounts of dust in the red. Now, as we advance the movie, you'll see that the background is low amounts of dust, although never zero. It's always a bit dusty. And then there are yellow and green blobs, circulation down in the surface, picking up dust, throwing it up into the atmosphere. There are explosions of dust that cover the entire planet, and we're just coming to one right now. This is an example of a global dust storm on Mars. If you were on the surface of the planet at this time, the sun would be obscured, you'd be looking horizon to horizon, and you'd see a glow in all directions. Our observations are going to look at the near surface, in which we're actually trying to understand how these storms get started. How do they go from the small to the large? Why some storms are small and stay small? That's the kind of data we're trying to get from MRO.
By closely examining atmospheric conditions, MRO will better protect future missions to Mars while guiding them directly to potentially rich sources of water. But NASA wants MRO to dig even deeper. Aboard the reconnaissance orbiter is a powerful new subsurface radar called SHARAD. It will give Mars a sort of body scan, enabling scientists to peer far below the planet's skin in search of water and ice that may still be trapped in the rocks below.
So far, we've been scratching the surface a few centimeters or probing only even microns. What your eye sees is just the veneer, just the surface of that. And now we want to get into that, but it's wide open as to what we're going to find.
The SHARAD instrument, or shallow subsurface radar, will bounce radio waves about 1 kilometer into the planet's crust. Receivers on board MRO will record and analyze the echoes to map the subsurface layers. The depth and composition of the planet's geology can be determined by the length of time it takes each of the signals to reach the spacecraft. With SHARAD, scientists hope they'll be able to detect ice or water in subsurface layers as thin as 10 meters. Until now, the European Space Agency's Mars Express orbiter was the only spacecraft equipped with a ground-penetrating radar called MARSIS. It can penetrate roughly 5 kilometers below the surface of Mars and has already found evidence of subsurface ice in small areas. MRO's SHARAD antenna will be focusing on shallower layers than the Mars Express, but will return much higher resolution images. It will be used to study underground layers of ice, rock, and possibly water that may be accessible from the surface. It will also probe the internal structure of the planet's polar ice caps.
We want to see whether or not that top part of the surface, which we know has some water ice, whether that's just the tip of the iceberg or whether it's actually the top of a much deeper permafrost zone. If it goes very deep, it actually might contain water that was in the atmosphere very early in the planet's history. So there would be a clue as to what the climate was in the ancient past and how it's changed over time.
The Mars Reconnaissance Orbiter will be a key component in laying the scientific groundwork for future missions to the planet. It will help to find landing sites for manned flights to Mars. The Mars Reconnaissance Orbiter promises to reveal many new secrets with its powerful suite of instruments. But it's just a stepping stone in our quest to better understand the Red Planet. NASA is already preparing future missions to Mars.
MRO is crucial for future missions. It's really a cornerstone of the Mars program. The data that MRO will return will enable us to choose where we want to land with future landers. When you think about it, over the next decade, we might have one lander, maybe two, and on an entire planet, where are you going to put them? You certainly want to put them where it's scientifically interesting to go and where it's safe to go. And both of those questions will be answered by the data that we return from MRO.
NASA's next planned mission to Mars is a reconnaissance trip to its North Pole. The task will be undertaken by a new lander known as Phoenix. The launch date is summer 2007. It will make its descent close to the permanent polar cap, where there is an abundance of ice, but also extremely rugged, forbidding terrain. The Phoenix lander is part of NASA's Scout program. At the polar cap, it will conduct experiments on the ice-rich soil. If the Phoenix data shows signs of life on the Arctic plain, future rovers will be sent in to investigate further. In 1999, the Mars Polar Lander was sent to a similar region at the planet's south pole. It vanished during landing and was never heard from again. Mission planners for Phoenix hope to avoid the same fate by identifying the most promising landing sites with help from MRO.
The Mars Reconnaissance Orbiter will do two things for Phoenix. First of all, it will certify the sites. They'll pick out their landing sites before we arrive. They'll have a primary and a backup. We'll take a look at those with our higher resolution, and we'll say, yep, that's a safe place to go, and it's a scientifically interesting place to go as well. We do that about 8 months before they launch. When they're on their way out, we'll also be looking at the atmosphere with our instruments, and we can give them an early weather report as to whether they've set the parameters for their entry, descent, and landing systems appropriately.
Once on the surface, Phoenix will dig small trenches in the layers of polar ice with a robotic arm. Samples from the trenches will then be tested in an onboard laboratory to see if they contain any of the organic compounds needed for life. This is just the first phase of what some scientists have dubbed a follow-the-carbon strategy. Since NASA confirmed Mars once had water on its surface, the odds are much better that life may have been able to develop here and that the remnants of organisms are still preserved in the planet's icy, rocky crust. The next vehicle poised to search for these life forms will be the Mars Science Laboratory, set to launch in 2009. It combines the remote automated field lab with the roving capability of Spirit and Opportunity.
What we're doing on the Mars Science Laboratory is we're changing the focus of the science investigation. Whereas Spirit and Opportunity were there primarily to look for evidence of water, which they found, which was great. Mars Science Laboratory is going there to look for evidence of organic matter.
MSL will be a much larger rover than its cousins Spirit and Opportunity, capable of driving more than 30 kilometers in search of organic matter. But the additional weight of its power sources and onboard lab will make it much harder to land safely.
Vehicle is now in top of Martian atmosphere. Lost. Continue to increase for 6 minutes.
To get MSL to the surface, engineers had to come up with an entirely different approach, known as a sky crane landing.
Instead of putting the rover on top of the landing platform and landing it, we actually turn things around, where we put the propulsion system, the rockets, on kind of like a jetpack on the back of the rover. And when we come off of the parachute, the rockets in this backpack slow us down. They bring us from about 1 kilometer up in the air down to about 20, 30 meters off the surface of Mars. At that point, as we're still coming down, we lower the rover on these cables. And now we've got this rover with its mobility deployed, basically ready to drive, hanging from ropes off of this rocket platform. And we just continue our descent until the rover touches the ground. The computer on board senses that landing, cuts the ropes, and there you have the rover sitting on the surface, and all we have to do is pop up our antennas and our cameras and drive away.
MRO, Phoenix, and MSL are part of an ambitious plan to return Martian soil samples to Earth and eventually to land humans on this forbidding planet. These missions face a vast array of challenges. But a key step in the process is determining exactly where on the planet humans should go.
When you're thinking ahead to future missions, including human missions to the planet, a key issue is what resources do I have there? I don't want to lug everything from Earth if I've got things that I can use there. Water is a key one of those. There's also the aspect of what's the surface made of? What kind of minerals are there? Knowing what that environment is, that also helps you plan the habitat. We're getting the basic set of information of the environment to help people make those assessments. What's risky, what's not, what do I have to prepare for, what can I live with?
The Mars Reconnaissance Orbiter should begin the science phase of its mission in November 2006, when it finishes aero-braking against the Martian atmosphere into a low-altitude orbit. In the meantime, scientists will continue to wring as much information as they can from the remarkable little rovers on the Martian surface. No one knows when Spirit and Opportunity will give out. Both rovers have far outlasted their expected lifespans and are still in working condition. But there is no way to clean them, and a buildup of Martian dust on their solar arrays may cause them to waste away. There is also the possibility that one of their critical electrical components will stop working. The rovers may stop responding suddenly and never be heard from again.
It's going to be hard, you know. I mean, when these things die, I won't lie to you, it's going to be a very hard day for us. And it's because they've accomplished so much. You know, if they had died young, if they had died shortly after we got them to Mars, that would have been hard to take. But they've accomplished so much that I think when we do finally lose them, they will have died very honorable deaths.
With the guidance of NASA scientists, the Mars Reconnaissance Orbiter will take the next great leap in Mars exploration. Mapping the surface, chasing the water, and searching for evidence of life on the red planet.
The fascinating thing about Mars is every time we've looked at it with new capabilities, we see new things. Mars keeps revealing just a little bit more every time we go and we probe.
In 2010, when we finish the MRO mission, we will have rewritten the science books on Mars.
And next on Discovery Science, see that the plan for getting man to Mars in full swing. Race to Mars follows, then at 10 we've got a passport to Pluto.